This problem is a motion equation or Suvat example problem. And it says, if my car can go from 0 to 60 miles per hour in 5 seconds, what is the acceleration of the engine? And part B, how far did the car travel? And this is part one of the problem. The first thing we should notice right away is there's a conversion issue, meaning we have 60 miles per hour, and we need to put that in usually the more conventional units of meters per second. So I'm just going to write this over here and do a little conversion for us. We're going to have 60, we have miles per hour. And again, we can convert whatever we want to first. So if we want to convert the miles first, we hopefully can remember that 1 mile, that's MI, is 1.609 kilometers. Then we cancel our units and we have kilometers per hour. That's still not what we want. So we're going to convert to kilometers. So we want to make this into meters somehow. So we got to know, okay, well, I have 1 kilometer. Again, I have to put the kilometers in the bottom so they cancel. And the equivalent distance to that is 1,000 meters. And I get that off. Now, you can get these conversions off of the internet using Google. You might have a conversion sheet. There might be something in your physics data pack, but at least use something that you know that's relatively accurate and use a factor label method to cancel those off. Now, we're in meters per hour. We usually want to get that in the meters per second. So now I have to convert the hours. And in this case, 1 hour will now go on top. Here, when we were converting, we put the thing we were converting on the bottom of the fraction bar. Now, because hours is below that fraction bar, we have to put it on the top of that. So again, I'm canceling the hours off. My hour equivalent time unit is 60 minutes. Now we're in the meters per minute, and we want to convert that one more time. 1 minute is 60 seconds. And that's going to get us into meters per second. When I cancel the minutes off here and here. So probably a better way of doing that would be to circle these units. 1 meter here, 1 second there. I'm just going to erase this on the end because I really don't want that quite yet. And then I know when I multiply all these together, I end up with, looks like 2 significant figures of 27 meters per second. So that's just how to convert it again, just give you another example to kind of see that. Now, I like to draw pictures. I like to say, okay, I'm going to draw in my case, I don't have a car, I drive a van. I have a family, I feel kind of old, but whatever. Here's my bad-looking van. Its initial velocity, u, is equal to 0. Its final velocity, now that we converted it, is 27 meters per second. We decided there's a time interval that this happens. That is 5 seconds, and that's to go that whole distance. So the next step is picking an equation. And our first equation, the v is equal to u plus a times t, is a very good example because it fills in everything but what we're looking for, which is the acceleration. Fill in my numbers, 27 meters per second is equal to 0 meters per second plus a times 5 seconds. And when I divide 27 divided by 5, obviously this goes away here. 27 divided by 5, a divided by 5, a times 5 divided by 5, a will equal 5.4 meters per second squared. So that's the first part of our problem. What is the acceleration of the engine? 5.4 meters per second. Every second that your car is accelerating, its speed will increase by 5.4 meters per second. Part B is how far did the car go? So now we want to know what S is. So I'm going to just pick a different color here. Kind of work up on this corner. S is our unknown variable. Our second equation, S equals ut plus 1/2 at squared, is our best candidate again because all we want is how far. Our u again was 0, so we have 0 times 5 seconds plus 1/2 times our acceleration we just found, 5.4 meters per second squared. times 5 seconds squared. And you'll notice seconds squared will cancel seconds. These have no units, so we end up with just meters. So the dimensional analysis of this is pretty simple because you can see the two multiplying and canceling each other off. Then when you multiply those numbers together, you get 67.5 meters, which with our significant figures is about 68 meters. So to get going that speed, it took 68 meters of distance to do that. So the second part of this problem now is if a deer comes walking into the road. If you live in Wisconsin, you know in the fall of the year, especially, you're always on the lookout for deer, knowing if you have to stop your car suddenly. And if a deer would suddenly come to this road, what is their new acceleration going to have to be? So we kind of have a different set of conditions. So again, I like to draw a picture. Hopefully I can do a better job of my van this time. And not really, but there's my van going. Now my initial speed, sorry, not V, but U, is equal to 27 meters per second. I'm already up to speed. I want my final speed V, which is down here by the deer. There's very bad deer, by the way, but there's our deer. We don't want to hit that. Our V at the end wants to be 0 when we get to that deer. Our distance between the two is 40.0 meters. Now we're taking reaction time and all that stuff out of this. We're saying I'm exactly 40 meters away. I'm putting on my brakes. And we're assuming the acceleration is constant, but we don't know what that is. So 40 meters is S. We have U. We're looking for the acceleration that is necessary for the brakes to stop the car before the car travels 40 meters. There's no time involved this time. So this time we use our last equation. Our V squared equals U squared plus 2 times A times S. Again, looking at our picture, it's a great way for us to kind of see where our information is and what we have to use. We want to end up with 0 meters per second squared is equal to 27 meters per second squared plus 2 times A, we're looking for that, times S, which is 40 meters. So just kind of plugging in our numbers and getting stuff out, this comes out to be 729 meters squared per second squared plus, not 2, I want to make that 80. Get out of here quick. 2 times 40 is 80 meters times A. And this becomes 0 meters squared per second squared. So when I take this over, I get negative 729 meters squared per second squared. Notice I had to subtract the same units from another one. 0 meters squared per second squared minus 729 gives me negative 729 meters squared per second squared. That's equal to 80 meters times A. Now if you kind of look, when I divide both of these sides by 80 meters, that's just going to cancel the squared off and end up with meters per second squared, but it's negative. My final answer here, the acceleration is negative 9.1 meters per second squared. Negative accelerations basically tell us that our speed is changing from a negative 27 down to 0. So I have a positive positive velocity, a negative acceleration, so it's just going to slowly take that number down to 0. If this acceleration persisted past the point of stopping, or the stopping point, it's going to slowly make my acceleration become negative and go in the opposite way. So a negative acceleration here, because our brakes are eventually going to stop, the car will stop moving at that point. But if this is like a car going up a hill, and the hill doesn't change slope, the car would start to roll slowly back down the hill, or maybe fastly back down the hill. 9.1 meters per second squared is a pretty fast acceleration. We'll fastly go down the hill the other way. So that's our Suvat equation example.